Welcome back, everyone, to part 4 of chapter 9. We are continuing our discussion on momentum, and what we need to do next is consider what it means to conserve our momentum. And remember that key word that we had out in front in the previous video of linear momentum. And that word is going to be very important to us because our definition of momentum is a vector. And to conserve momentum, like every other conservation law that we've had up until now, states that what we start with is what we end with. So for a closed system, the momentum that we start with has to equal the momentum that we end with. Well, so what does that mean for a closed system? Well, a closed system could be just one mass. If that's the case, if all we ever have is one mass in the system, then the momentum of that mass can never change. And this follows suit with the first law of motion that says that an object with constant velocity will maintain constant velocity unless it is acted on by an outside force. Well, the only way that we can have an outside force act on our object is to bring another object into play. And so if we now have two or more objects within our closed system, so if we have mass 1, mass 2, and if these two masses interact with each other, that interaction can cause a change in momentum for each object individually, but the overall change in momentum for the entire system must be zero. In other words, the momentum that we start with for each of these masses, I want momentum terms here. The momentum of mass 1 plus the momentum of mass 2 before any interaction must equal the combination of the momentums before and after the collision. I need to change my subscript there. All right. And then if we rearrange the terms here, we can subtract the initial momentum values over to the other side. And what that will do is it'll produce those delta statements that we had right there. So any change in momentum for the system must equal zero. That's what our conservation of momentum says. But that doesn't mean that individual masses have to maintain a constant momentum. We can transfer momentum between two or more objects in a similar way that we could transfer energy back and forth from an object. So that's what we need to consider in this video, is how does that momentum transfer? Well, it's going to transfer through the interaction of force between the two masses. But then after those forces have played their part, whatever change in momentum we have for one object is going to have to be equal and opposite to the other object. And by doing so, by being able to conserve the momentum before and after these collisions, we have equations that we can set up. We'll jump into an example problem here. A really good example problem for momentum is billiards or playing pool. And so let's say that you have a cue ball. So this will be mass 1. And you're going to strike the cue ball. You'll give the cue ball some initial velocity. And that cue ball is going to strike another ball on the table. Really doesn't matter what the other ball is. We'll just call it mass 2. But typically when you play billiards, the only ball that should be in motion is the cue ball. And so the initial velocity of the second ball will be stationary. Now, when it comes to billiards, especially with the more common billiards tables that you'll find at pool halls or bars, there is a slight difference in the mass between the cue ball, the mass of a cue ball, and the other balls on the table. While all the other balls usually weigh 0.16 kilograms, 5.5 ounces. All right, so I just Googled the values, and the cue ball is going to be about 0.17 kilograms, but then all the other billiard balls will be just a little bit less. And this is actually a design feature, because whenever you play billiards and you sink one of the balls into one of the pockets, some of the billiard balls that you have, like in a bar, will have the ball collector. So if you sink one of the solids or the stripes, it will start collecting them. And the only way that you can get them back out is to put in some more quarters. But if you sink the cue ball, that cue ball is supposed to roll all the way down to the ball deposit. And so how does the table know the difference between the different types of billiard balls? And there's actually a slatted track inside the table, and that slatted track has an opening right along the middle of the track that is just wide enough for all of these billiard balls to fall through. But given that the cue ball is of a slightly larger mass, that means that the radius of the cue ball is going to be slightly larger as well. And that prevents the cue ball from dropping through the slat, and it's able to roll through to the ball deposit, and you can keep playing your game. So that's another good thing about this example, is that given that the cue ball is not the same mass as the other ball on the table, we're not going to have a perfect transfer of momentum. In other words, the final velocity of the second ball is not going to equal the initial velocity of the cue ball. And what I mean by that is that a lot of times when you're playing pool, you'll strike the cue ball. The cue ball will collide with the other ball on the table, and then the cue ball will basically just come to a halt, and it'll have a final velocity of 0 after the impact. And then the other ball travels off with some final velocity. Now, if the masses of the two balls were the same, given that these two velocities are 0, the momentum that we start with in the system has to equal the momentum that we end with in the system. So what do we have here? Well, we have mass 1 times its initial velocity plus mass 2 times its initial velocity has to equal mass 1 times its final velocity plus mass 2 times its final velocity. Because these two velocities are both 0, that says that there's been a 100% transfer of momentum from the cue ball to the other ball on the table. Let's give the other ball, we'll say it's the 8 ball. Well, if the mass of the cue ball is slightly larger than the mass of the 8 ball, then the only way to maintain a numerical equality is that the final velocity of the 8 ball is going to have to be larger than the initial velocity of the cue ball. And we can do this just by plugging in some numbers. Let's say that the initial velocity of the cue ball was 10 meters per second when it collided with the 8 ball. 8 ball was stationary, and so if I want to know the final velocity of the 8 ball after the collision, all I have to do is divide each side by mass 2, and I'll have my answer. The cue ball, mass 1, was 0.17. The 8 ball has mass 0.16. We had an initial velocity of 10. We'll get our calculator out. Got to open my calculator app. 0.17 divided by 0.16 is Oops, I had some extra stuff going in the calculator there. Let me clear that out. 0.17 divided by 0.16 is 1.0 excuse me, 1.0625, and so since we're multiplying that by 10, this becomes 10.625, and that is going to be meters per second. And so the 8 ball ends up traveling away from the collision with a higher velocity than what the cue ball had, but that's because the 8 ball had a slightly smaller mass. All right, well, this is our conservation of linear momentum. This is how we're going to do this. This is a one-dimensional version of the problem because everything that has occurred in a straight line. I can set up a reference frame, and with that reference frame, I see that everything is either 0 or pointing in the positive direction. All that's left for me to do is to make sure that we are maintaining both the numerical equality and the direction of our vectors. Well, the numerical equality has already been taken care of right here. We've solved for the necessary value to make this a true statement. The other part is making sure that the direction has been conserved, and that is also evident in the picture. We started with a momentum that was traveling in the positive x direction, and we ended with a momentum in the positive x direction. And so this idea of conservation of momentum is really not that difficult to grasp. What makes it a bit challenging is when our systems go from being one-dimensional to two-dimensional or three-dimensional. So let's try the same billiard table, except now when we strike the cue ball with its initial velocity, it's going to strike the 8 ball with kind of a glancing shot. And after the collision, so the 8 ball will be stationary before the collision. And then after the collision, the 8-ball is going to be deflected down and to the right with some final velocity. And the cue ball, there's a couple of different options as to what might happen. The cue ball could be deflected up and to the right. It could be deflected up and to the left. But in this case, I'll just pick a direction that cue ball is going to travel after the collision. And now we can see that our job of maintaining a conservation of momentum is going to be a bit more challenging. But this is not something that we need to really stress over because we've done stuff like this with vectors before. We know that instead of trying to tackle a two-dimensional or a three-dimensional system all at once, it would be far easier if we could break these vector systems down into x and y directions, respectively. In our case, we have a two-dimensional system where we're basically looking down on top of the billiard table. So this is an overhead view. We're assuming that the billiard table is flat and horizontal, so we don't need to worry about a z-axis right now. But we can take care of this conservation of momentum by addressing each axis individually. We can then put those back together to get the final momentum of the system. So let's see what that's going to entail. We need conservation of momentum along the x direction, and we need conservation of momentum along the y direction. And that means we need to have established x and y axes. We'll go ahead and do that. We will allow the right to be our positive x direction, and I'll assign up to be the positive y direction. Now, again, that we're looking down on a flat surface, but well, this makes for an interesting discussion because as far as our reference frame is concerned, everything before the collision just has momentum in the x direction. Mass 1 is moving in the x direction, mass 2 is stationary. There is no momentum in the y direction. But then somehow after the collision, we have each of our vectors with components. Some of those components are in the x direction, but some of them are in the y direction. How do we magically go from having zero momentum to obviously having momentum values in the y direction? Well, we can have this as long as the components that we're adding together equal 0. And that should be evident now by looking at the directions that those y components are pointing. We have one component that's pointing in the positive y direction. We have one component that's pointing in the negative y direction. And the only way that this can happen is if these two components of momentum add together to make 0. All right, let's see what we have going here. I'm going to backtrack a little bit in my work, and we'll focus on just the x direction of our momentum for right now and see what this produces. So what momentum we start with has to equal the momentum that we end with. I'm going to write all of this out in general form, then we can plug numbers in later. We have two masses involved, so the initial momentum of mass 1 along the x direction plus the initial velocity of mass 2 in the x direction. I can drop the vector notation because everything is occurring just in the one direction of x. After the collision, our cue ball and the 8 ball have components that are running in the x direction, but I need to figure out what those are. To do that, we will assume that we know the angles that each mass has with respect to its final velocity vector and the x direction. So these final velocity vectors, v final 1, v final 2, they are making some angle with respect to the x direction, and that is what is going to allow me to find the components of those two. But each of those are going to utilize the cosine of the angle. Now I have theta 1 and theta 2 respectively because right now I have no idea as to what those angles are going to be. Again, this is a general solution. We can always plug our numbers in later, but it's always best to have a general solution available. After the collision, we have in the x direction mass 1 traveling with v final 1 cosine theta 1. That provides us with the x component of the final velocity for mass 1 plus mass 2 times v final 2 cosine theta 2. That provides us with the x component of final velocity mass 2. Now, these two expressions were added together. Why? Because each of them is pointing in the positive x direction. So they will combine as an addition. That is our conservation of momentum equation for the x direction. We will now move on to the conservation of momentum along the y direction. Now this one should go a little bit quicker because, as we said, starting off we had no momentum in the y direction. Mass 1 had all of its initial velocity in the x direction and mass 2 was stationary. We could always generalize this if we wanted to. We could say mass 1 has some initial component in the y direction for its velocity. Mass 2 has some initial component for its velocity in the y direction, but we already know that those are both 0. Then, after the collision, we need the momentum values after the collision. This is where we're going to see a difference in the values. We have mass 1 with its final velocity component. Now our x components both utilize the cosine, so these y components should be utilizing sines of the respective angles. There's mass 1 and its final velocity component in the y direction. We have to subtract from that the momentum from mass 2 because it is pointing in the negative y direction. That's going to be mass 2 Final velocity 2 sine theta 2. All right, so there are the two equations that we have that describe the conservation of momentum for this two-dimensional system. And obviously this is quite a bit more complex than what we had for the one-dimensional system. But I want you to take a look at this general solution that we have for the two-dimensional system and ask yourself, for a system of equations, we have two equations. How many unknowns can you have in a system of equations? And the answer to that is that the number of equations should equal the number of unknowns. Well, how many unknowns do we have in this system of equations? If we want to use the same masses for the cue ball and the 8-ball, we can, but we could just as easily use some other system of masses. So we have mass 1, we have mass 2, which could be unknowns. We have the values of the initial velocities, which are unknown. We have the values of the final velocities, which are unknown. And we have the angle relationships that are unknown. We have 8 unknown quantities within these two equations here. The only way that we would be able to solve them is if we had 6 of these pieces of information. Now, shouldn't matter what 6 pieces of information are given, but all of these pieces of information are going to have to fit together perfectly into this system of equations. And now I think you can appreciate why I've chosen not to throw some random numbers into this problem, because in doing so, I can almost guarantee you that it's not going to work out right. There has to be a perfect balance with all of these numbers in order for them to make for two true statements. And my brain can't do that many steps ahead. But that's okay, because we have a general solution set sitting in front of us, ready to go for when we are given, let's say, 6 of the 8 pieces of information. So if I gave you mass 1 and mass 2, if I gave you the initial velocity of mass 2, the final velocity of mass 1, and the final angles for mass 1 and mass 2, could you tell me the initial velocity of mass 1 and the final velocity of mass 2? And, well, those are 2 unknowns. We have 2 equations. Yeah, that can be done. I just can't do that in my head and expect this to turn out right. But let's consider what we do have available to us right now. We said that we had the masses of the 2 balls. We have the cue ball and the 8-ball. So we have those 2 values right there. And we said that the initial velocity of the cue ball is 0. So we can plug that in. If we get a 0 for the initial velocity of mass 2, then we can drop the 2 initial terms for mass 2. We also said that mass 1 does not have any momentum in the y direction before the collision. And so we can drop that portion from the second equation. And that justifies to us that the 2 momentum components of the billiard balls after the collision have to add together to equal 0. And this helps us to gain some information about the relationship between the two billiard balls. We know that whatever mass, velocity, angle combination, those combinations are going to have to equal each other in magnitude. All right, so that is a two-dimensional example of conserving linear momentum. Again, if we can take this two-dimensional system and break it up into two one-dimensional problems, we're going to have a much easier time. As long as we're given enough of the information in the system, we can always come back and fill in the missing pieces with the algebra. But since these problems are so delicate in terms of how everything has to fit together, I don't want to press my luck in trying to do an example problem with these. Instead, I will leave that to you with your homework sets. Instead, I'd like to move on to a different example problem where we have a single billiard ball which is moving towards the wall of the billiard table. So right here we have the wall of the billiard table. It will strike the billiard table at what we call an incident angle of theta. And then it will rebound with the same angle theta and a final velocity, v final. Now, since we only have the one billiard ball, we don't really need the subscript of 1. So we're going to say that this billiard ball of mass m, we'll go ahead and use the mass of the cue ball just to make this a bit more realistic. We'll say that the incident angle is 30 degrees and that the momentum in the x direction doesn't change during the collision. What is the impulse of the ball? That's our first question. And if the collision took 0.05 seconds, what is the average force on the wall from the ball? So those are the things that we want to know. Oh, impulse. We've heard that word before. What's impulse? Well, impulse was J, but J was defined as the change in momentum for the system. And again, this is written in vector form. If we prefer, we can break that up to ask how much has the momentum changed in the x direction and how much has the momentum changed in the y direction. And then we can put those two back together. Average force. We've heard about how average force can compare to changes in momentum and time. And such, if we can find the change in the momentum for the ball, we'll pair that up with the time interval and we should be able to find the average force. So let's get started. This is a two-dimensional system, and we have actually been given a generous amount of information here, believe it or not. We know the mass of the ball, we know the angle, and we're told that the momentum in the x direction does not change. Momentum is directly related to the velocity of the object. Let's focus on these velocity vectors. For the incoming velocity vector, we have one component of the velocity that is heading towards the wall. Can't quite get an arrow out of this. Try again. So we have one component of the velocity that is headed right towards the wall. We have another component of the velocity that is running parallel to the wall. After the collision, our final velocity has a component that is running parallel to the wall and a component that is pointing away from the wall. We were told the momentum in the x direction does not change. So any change in momentum before and after the collision for the x direction is 0, or the x component of momentum before and after the collision have to be equal. All right, so what does that mean for us? It means that with the same mass, these two velocity components have to be equal to each other. We have the same angles for each vector. They're both 30 degrees. And if those two pieces of information are the same, that means that each of these vectors will have to have the same magnitude. I can put together the information about the x components of these velocity vectors along with the angle, and I can solve for the magnitude of each of these velocities. I'll use the right triangle for the initial velocity vector. We have an x component of velocity, which will have to equal the initial velocity magnitude times the cosine of the angle theta. But that means that if the two components of velocity in the x direction are equal to each other, then the magnitudes of the velocities have to be equal to each other as well. So that's the first bit of information that we get out of this system. If both of these velocities have the same magnitude, then I'm just going to start calling both of them v. The only difference between the two vectors is that we have y components that are pointing in opposite directions. And this might be a very good time for us to specify what the positive directions for this problem should be. I'll let to the right be the positive x direction. That will keep everything about my x components in line with what I have right here. But now I can see that a change in momentum for the y direction is not going to equal 0 because I do not have the same momentum. In one case, the momentum is positive. In the other case, the momentum is negative. So let's see what that does to our change in momentum for the y direction. A change in momentum for the y direction is not equal to 0. We can extrapolate what the components of the initial and final y momentums need to be by using information about the the y components of the initial and final velocity vectors. So this velocity component is going to be v naught sine of theta. This velocity component is v final sine theta, but the magnitudes of the velocities are the same. So what we really have is v sine theta and v sine theta. This one is positive because we're going to have a positive momentum. This one is negative because we're going to have a negative momentum. All I have to do is sneak in the mass of the ball, and I have the initial and final components of the momentum. We have a final component of negative mv sine theta. We have to subtract the initial component of mv sine theta. That does not equal 0. That equals a negative 2mv sine theta. That is the change in the momentum for the y direction. That value is going to go right in here, negative 2mv sine theta. What was the change in momentum for the x direction? Well, we already said, doesn't change. So the change is 0. We have no change in momentum for the x direction. We have a change of negative 2mv sine theta for the y direction, and that means that the overall change in momentum, or impulse, as we called it, is negative 2mv sine theta j hat. Everything that we're dealing with in terms of momentum and impulse are vectors. As such, they have to be treated according to vector direction. When the billiard ball strikes the table, the only change in momentum is along the y direction. There was no change along the x direction. So how does the billiard ball change its momentum in the y direction? Well, that's going to happen because the wall is going to push on the ball. Our billiard ball started by having a y velocity that was carrying it towards the wall, but then during the collision, the wall pushed the ball away, and that is how the ball was able to reverse its momentum along the y direction. So how much force do we have? Well, here's the equation. The average amount of force involved is going to equal the change in momentum over the time. The change in momentum is right there. We're calling it the impulse. We have negative 2mv sine theta all over the time interval of 0.05 seconds. At this point, let me see, we have the mass, we have the angle, I guess I would have to give you at least one of these, obviously, since they're both of the same value. We'll say 5 meters per second. Negative 2.17 for the mass. 5. Sine of 30 degrees. 0.05. Calculator time. 2 times 0.17 times 5 times sine of 30 divided by 0.05 makes for a negative 17 newtons. So the ball experiences an average force of 17 newtons in the negative direction. Well, does that match up with the reference frame that we're using? And the answer is yes, it does. The ball would have to be pushed in the negative direction if we are to change the direction of the vertical, or not the verticals, excuse me, the y velocities. We shouldn't have any vertical discussion here since we're looking down on top of the billiard table. So is that it? Are we done? Well, not quite, because that's not what I asked for. I asked for the average force on the wall from the ball. What we have found right here, this is the average force on the ball from the wall. This is how much force the wall puts onto the billiard ball. I want the opposite, quite literally. And we can answer this very easy by using Newton's third law, which says that for every force, there must be an equal and opposite counterforce. If the force of the wall on the ball equals negative 17 newtons, there must be an equal and opposite counterforce that we can call force of ball on wall. And that would have to be of equal and opposite value. So there we have it. The wall produces a force on the ball, pushing the ball in the negative y direction, but during that impact, the ball pushes on the wall in the positive y direction. And that can be justified going back and using Newton's third law. So this is how we take care of conservation of momentum in 1 dimension and 2 dimensions. It does take a little bit of getting used to, but once we can keep track of everything, specifically keeping track of the vectors in the x and y directions, then it becomes a pretty straightforward vector problem. Now I'm going to end this video here, but I am going to make a 5th video that covers some example problems dealing with collisions. And there are 2 types of collisions that we need to consider. We'll go ahead and define those right now. We have 2 types of collisions. The first type is what is called an elastic collision. The second is an inelastic collision. And once we get the definition of one, the other is pretty self-explanatory. But an elastic collision is a collision where mechanical energy is conserved. And so an inelastic collision is a collision where mechanical energy is not conserved. Case in point, our definition of mechanical energy is the combination of kinetic and potential energies, and that's it. Now we can have kinetic energy in the form of 1/2 mv squared. We can have potential energy in the form of gravity potential. We can have potential energy in the form of spring potential. And so all of that combined is the useful kind of energy that we call mechanical energy. And during a collision, it is possible to transfer kinetic energy from one mass to another. It's also possible to convert potential energy between two masses through that transfer of kinetic energy. Well, if we can conserve the mechanical energy in the system, that means that what mechanical energy we start with equals the mechanical energy that we end with. And that's it. This expression does not provide any consideration for friction, air resistance, drag. And so how realistic is it that you might have an elastic collision? And the answer is probably never. Because any kind of collision, any kind of interaction between two masses, there's going to be some amount of friction, air resistance, drag, especially for very energetic collisions. You could have sound, you could have light, you could even have some rotation involved. And all those things that I just mentioned can be represented using another form of energy that could be added on as a product to the right side of our conservation of energy equation. And that's what it means to have an inelastic collision. It means that what mechanical energy we start with is not conserved. We may still have some mechanical energy left over after the collision, but there's a very good chance that some mechanical energy has been converted into heat. Some of that energy could have been converted into sound. Some of it could have been converted into light. Some of it could have been converted into rotation, which actually rotation falls into the category of kinetic energy. And so that will actually be a form of mechanical energy, but we're gonna get to the discussions on rotational systems in chapter 10. So if we want to, we can just say we're going to sneak that rotational energy into the kinetic energy forms. But these over here, these are not going to be very easy for us to keep track of. And if we have a collision that results in a lot of heat or sound or light, then we're probably not conserving much of our mechanical energy. And if that's the case, then about the only thing that we can say at this point is that the mechanical energy that we start with does not equal the mechanical energy that we end with. Really, the only thing that we have for this definition is an inequality. And an inequality is pretty much useless in any kind of mathematical expression, because there's only one way to make an equality work. There are a lot of different ways that you can make an inequality work. But this is how we will be able to test to see if a collision is in fact elastic or inelastic. Now, like I said, this elastic case, this is really an ideal scenario. We could use this as kind of an estimate of what's going to happen in a system, assuming that there's very little loss of mechanical energy during the collision. But this is the real world situation down here. With inelastic collisions, we basically have to abandon the idea of conservation of energy. And I don't know about you, but I really like that conservation of energy stuff, because it meant that we could do a whole lot of the physics without having to deal with the vectors. But if conservation of energy is not going to work for us anymore, then what are we supposed to use? Well, we're going to use conservation of momentum, because conservation of momentum doesn't care about what form your energy is in. Conservation of momentum is going to be true regardless of the type of collision that we have. Even though momentum is a vector, and even though we're going to have to do a little bit of additional work to keep track of everything in vector form, it's something that we can do with the math. Whereas for inelastic collisions, well, there's really not a whole lot that we can do there except to say, nope, the energy before doesn't equal the energy after. So that fifth video, we'll look at some example problems, and we'll ask the question, when is it good to use the different conservation laws? So when should we use conservation of energy versus when should we use conservation of momentum? So stop back and take a look at that fifth video, because those example problems will really help to solidify the ideas that we've spoken about here. So see you then.